This, well, maybe I can like do like that. Okay, it's like highlighting Annie for some reason, whatever. Anyway, hi everybody. We're going to start lecture now. How's everybody doing? Dead silence. Okay, good. I'm glad some of you are doing good. Hopefully some of you are doing okay. If you are like needing any help with anything on the homework or anything related to the course, please feel like you can reach out to us. Also, if you think we're doing a bad job, there's that anonymous survey that's on the B courses. You could just fill it out whenever you want anonymously and let us know how we're doing. We try to check that fairly regularly, just so that we take your input if you have any. Yeah, so it's week 7 of the Python DeCal. Some basic little announcements. Homework 5 was just due. And then also that the final project survey, which I was just yelling over and over again while we were waiting for class to start, that is basically due just now. It needs to be done absolutely before lecture is over, because that's when we're going to start making groups right after this lecture is over. So fill it out now, like ASAP, while I'm talking if you need to. We want to make sure that we put you into groups of 4 so you can work on your project. There's so many of you. Normally in the past, we would let you work in groups of 2 or 3 or alone even if you wanted to, but we simply just can't afford to do that. We don't have the time space available to us. So we have to put you in groups of 4. So think carefully about like what you want to do. You're not obliged to stick with whatever you say you want to work with, but it'll just give us a general picture of putting you with people that will best suit you as well as best suit your interests. So we'll try not to put all the freshmen in one group or in a couple of groups, so that you have somebody with a little bit more like knowledge and experience from the upper division courses. If you pick like something that's a bit more theory intensive or whatever that may be, we want to make sure that we have pretty evenly distributed groups with lots of ranges of skill levels, so that everybody can learn and gain something from those groups. Also, if you have preferences for who you want to work with, you can also state those there. Yeah, so start thinking about those final projects, start thinking of ideas. There'll be a time where we all come together and review your project ideas to tell you if they're too crazy or if they're too easy or if they're just right in the scope of the class and what's capable in this class time frame. So don't be afraid to come up with any ideas you want. We've had people attempt to simulate galaxies in the past with n-body simulations. We've had people simulate like proton collision scattering and like from quantum mechanics and stuff like that. Sudoku solvers, you name it. Literally like anything can go in here. Some things are a little bit out of reach. Like you probably won't be able to simulate fluid dynamics. That might be something that's a little hard to do. But there are a lot of things you can do, even with just simple basic Python knowledge. And to be quite honest, the skills that we've given you so far is already quite a lot you can do with it. You can analyze large amounts of data. You can make really interesting plots and observations about scientific findings. In fact, everything we've taught you so far is already, I can already guarantee you just about all of it is going to be used in your upper division courses somewhere, whether that be a lab course, like fitting curves, fitting models to your data, or pulling data from the internet and then loading it into a Jupyter notebook and plotting different model theories and stuff like that for stars. Whatever you may come across, it's all there. Yeah, and we're going to be forming the groups on Monday. So please come to class if you can. If you can't, come to Zoom and we will put you in breakout rooms that way. But we really strongly encourage you to come to class if you can, if you're healthy. Yeah, again, fill out the final project form. Very important. Any questions about that? How do we feel about curve fitting after homework 5? Good, medium, bad? Some mediums, some no hands at all. Okay, interesting. All right. Well, I hope it was somewhat helpful, but I don't expect you to become masters at anything in this class. This class is an introduction to it. So don't be discouraged if it's confusing. In fact, most of the things I learned the first time I took a Python class didn't really resonate with me until the 2nd, 3rd, 4th semesters of my undergrad. So don't worry if it sounded like a lot right away. And we'll also have review times. We'll probably have a review lecture here or there to go back on those topics and review them. Okay, cool. Let's get it started on today's lecture. Last time we covered a few different things. We developed the tools necessary to do numerical differentiation and integration. at least the scientific standard. In other words, we love SciPy. SciPy is the package, or like the giant package that houses all those tools. SciPy.integrate, SciPy.rootfind, SciPy. Blah blah blah. SciPy is a great package, just like NumPy is, that specifies more in like scientific tools. NumPy is really good for like numerical, like mathematical related things, like NumPy.mean, standard deviation, using those arrays, Fourier transform, stuff like that. But SciPy is really where SciPy really shines, is like numerical methods like differentiation, integration, curve fitting, all that's good stuff. So SciPy, this is kind of like, we're starting like a really big arc in this course of like how to eventually run simulations and make video games. But in order to do that, we need to understand mathematical tools like integration, differentiation, and today we'll be covering differential equations. A key takeaway from yesterday's or Monday's lecture is Gaussian quadrature is the best method to take the integral. So, and anytime you do a numerical integral, it's all Riemann sums. You learn those in high school. It's like doing the little rectangles under the curve and adding them all up. But Gaussian quadrature is like a really fancy method to do those rectangles, and they're not all the same because it's quadrature. It's really confusing. But other people coded it up, so you don't have to understand it. Just know that it's the best one. That's it. Gaussian quadrature is the best one. So every time you use an integral, do dot quad. It computes it in like a quarter of the time with a quarter of the error, or a millionth of the error, or whatever. It's really good. Sorry, was there a question? Okay, cool. And then lastly, numerical derivatives are much easier to compute than integrals. So just kind of like the same idea with like normal pen and paper calculus. You could just about take a derivative of any function, but you can't take an integral of any function, right? So some integrals tend to be more expensive or more difficult to do than a numerical derivative. Cool, and we use SciPy to compute them. Now let's get into today's lecture. So we're going to talk about differential equations. It's a very fun topic, and it's close to mine, or my heart. There they are. And they basically govern how like all of the world works. So anything that changes with respect to time, probably a differential equation governs that. So that might be fluids moving through a gas chamber, or air moving around a car. That might be stars exploding. That might be gas flowing onto a star to like create it, or a black hole for that matter. I mean, the air we breathe, like the springs we use, differential equations run everything. In fact, like there's a common saying, and I think it's just like in any physics class, that almost all of the universe can be like approximated to either a spring or a string. Like you can basically, like you'll learn that in all your physics classes. If you take more and more physics classes, you always use springs and strings to model everything. And those are governed by differential equations. And we're going to learn how to use those on a computer, how to solve them with Python. They're pretty cool. So differential equations, they govern the world, like I just said. You've probably already seen them in your classes if you've taken any physics classes or calculus classes. For example, dx dt is equal to velocity. d2r over dt squared is like the force over mass. That's just like Newton's second law, basically. This one down to the left is like the heat equation, really nasty. You'll probably learn that in like thermodynamics. Those two, where they have like the straight D, those ones are ordinary differential equations. And then the ones with the curly D's are partial differential equations. And the reason why they're different is the number of variables that you can differentiate with respect to. So an ordinary differential equation usually only has like a single variable you can differentiate with respect to. So dx dt, there's only like t is the only independent variable in this equation. Same thing with this one. And r is the dependent variable. Whereas this one, you have multiple variables that you can differentiate with respect to. So that makes it more complicated inherently. So you ask like, how does my function change when I move one variable but not the other variable? Or what if I move both of them? That's where it gets a lot more complicated. And we'll talk about that later. We're not going to actually do partial differential equations in this class. There's upper division math courses dedicated solely to solving these on a computer. I'm not gonna, this is far above my wheelhouse. But we can talk about the ODEs. Those ones are a lot easier. That's like what governs the spring. So just to summarize, ordinary differential equations are easy-ish. Partial differential equations are really hard. And people spend their whole lives studying how to solve them. So we'll skip the hard ones. We'll do the easy-ish. They're not easy, but they're much easier than the PDEs. So I think the easiest way to go about solving a differential equation, the easiest conceptual way, is Euler's method when we do it numerically. There are ways to solve it with pen and paper, but oftentimes Euler's method is the best way to do it for a computer. Or not the best way, but at least the easiest to understand. We'll see that there's better methods that could do it much better and faster and more accurately, but we'll start with Euler's method and build our way up. So Euler's method is very similar to that numerical integration idea where you're adding up all the rectangles under a curve. You're discretizing it is what we call, and it just becomes a sum where you add up all the areas. In this case, it's a little different. We still break it down into segments. See this blue curve. The yellow curve is the real curve. The blue curve is breaking it up into little segments. We always have to specify initial conditions. So you have to tell your program where you're going to start. If you don't tell it where you're going to start, how does it know where to start? So that kind of makes common sense. And then you need to start from somewhere. And then also the number of initial conditions you have is the order of your differential equation. So a first order differential equation means I only need one initial condition. Similarly, a second order differential equation means I need two initial conditions. First order would look like the one on the left right here, dx dt v of t, and second order would look like the one on the right where you're taking like a second derivative. Okay. You also need to specify your step size that you're taking. So how big of a step are you taking? Typically, the smaller the step size, the more accurate your differential equation solver is. But again, you can only go so small before you start to burn your computer. I don't literally mean burn it, but it'll take a long time. You don't want to use 10 billion steps. That would take forever. But you also don't want to use 10 because then you wouldn't get the right answer. So you have to find the sweet spot. Yeah, and then remember to assign your variables, not append them. I don't remember why I said that. It's fine. It's not important. We'll go to the next slide though. So this is how you would write it up in code, like the naive way, and we'll walk through it. There's a lot of code I just threw at you, but I'll just direct your attention to the big equations and then the left side first. So looking at this big equation, this is the one. This is the differential equation we want to solve. Dy dx is equal to x times y. Might have seen this like in a calculus class and try to solve it with your pen and paper. We're going to do it numerically. We start with initial conditions. X naught and y naught is equal to 2, 3. So saying that x starts at 2 and y starts at 3, and then we'll see how it evolves with over the variables we iterate. So over x, I guess you could say. We're going to see how y changes with respect to x. So on the left side, we start with the dx. That's like 0.01, like a really small incremental step. The smaller this gets, the more accurate we become. And then here's our initial values, 2, 3. We define a derivative function, which is literally just the right-hand side. We say that dy dx should be equal to x times y. This is what our derivative should be. Usually you get this just by doing your calculus on a piece of paper or something. And we're going to create an x array that we're going to iterate over, starting at like the initial condition and going to 5 with like 301 steps, just some arbitrary number, but to make it like small little incremental steps. And then we're going to set the y array equal to a bunch of zeros of the same length as your x array. And we're going to populate this y array with values that we compute. So at the end, you'll have an x array and a y array that like encapture the whole system once we iterate over all the values. So we set the 0th element of the y array list, or it's a numpy array. We set that equal to y naught. So we're saying that the start of our array is the initial condition. It makes sense. And then everything after will be how it evolves over time, or x, I guess you could say. So for I in range 1 through 301, so just saying we go, after you start at the initial condition, we're doing everything after all the way till the end of the array. We're saying that dy is just equal to the derivative, the x times y, of the previous item in our array. So it'll start with the x naught and y naught. We'll take the derivative by just multiplying them. And then we have to multiply by our differential dx. So in doing that, it's like breaking down this. You can, if you're not super rigorous with math, oftentimes in your physics classes, you can like look at those like fractions, kind of, or differential fractions, and you could just like multiply by a dx, and that'll just give you your dy. So if I multiply by a dx on the left-hand side, it would like cancel out with the bottom and give you a dy. And that's how much your like y changes by like a little dy amount. That's not rigorous. If you're a mathematician, I'm sorry. But I was told you can do that in physics classes, and everybody does it, so it's fine, I guess. Yeah, so now you have a dy value just by multiplying a differential dx, which is it's like a constant that we assign at the beginning. The smaller this is, the more steps you have to take. We just multiply that by what our derivative should be, x times y, of the previous step in the list. Then we set y equal to what it was previously plus this dy. And then you just repeat over and over and over, and then you put that in the list, and then you repeat over and over and over again. So we'll just start with this, like the very beginning, going through this. We set x naught, y naught equal to 2, 3. We start with an initial value in our array for x of x naught, and then it goes to 5. So x is like, we predefine, we tell it what x we want to look over. And then we start with a bunch of zeros in our y list, and we set the first value, or the 0th value in the y list, equal to our initial condition. And then so when I is equal to 1, starting this whole thing, then you call the derivative of 1 minus 1 is 0. So it takes the initial y naught value and then the initial x naught value, and it multiplies them. And then you multiply by that dx, that gives you dy, and you add, and you keep going over and over and over and over again, and it'll evolve your y array. That was a lot. Is there any question? Okay. I don't think so. If that's the case, then we'll keep moving. If you get any questions, please let me know. But this is going back to your calculus 1A, 1B level math. If you haven't taken that yet, oh yeah, there's a question.
When you do that for loop, you do 300 step 300 times. The y array has 301 elements, right?
Right. So yeah. So, but like what we do before that is we set the 0th element equal to the y naught, and then we just iterate the rest of the 300. Okay, does that make sense? Good question. Very good question. This is often something that like, when you're coding it up from scratch, it's like something that like easily breaks your code when you like, how do you, thinking about like which index is which. Very good point. Okay, let's move on to the next one. Yeah, so this is jank. That method is hella jank. It sucks. And I'll show you just how bad it is. So if you use it to say simulate the orbit of a planet around a star, you get something that looks like this. This is the left-hand side. You probably, oh man, you can't really see it that well. But so the left is would take 1,000 steps. The middle is 10,000 steps, and the right is 100,000 steps. Okay. This is the orbit, x-axis and y-axis, going around a central star. The red is the path. Everybody see that? Or can everybody see that? All three of them? It's kind of hard to see the other two. But this left-hand side, holy shit, that's awful. Look at it. It's like not even a circle. It's really hard to see. Look at the middle one though. The middle one's just as bad. Like it's not a circle. It's like moving outward over and over and over again. And look at the energy. Notice how that line like keeps going up. Orbits are supposed to be stable. Like a planetary orbit is stable. Like the energy is supposed to be like roughly constant. It's not supposed to like increase. That's weird. Like that's not good. If you are NASA and you're trying to simulate like, okay, if I need to get my rocket over to Mars and you use that model, you're sure as hell gonna miss it. You're gonna miss that. Like that rocket's gonna go way past Mars. You're not gonna hit it at all. So there's other methods that are better than that. Standard Euler, and like look at how many steps you need to take to even get to like a remotely good orbit. You need like 100,000 steps. That's awful. That's, yeah, and it's still going up. It's going up a little less, but it's still bad. So there's other modified techniques. I'm not going to go through each of one of them like step by step like I did with the Euler. The Euler is just for you to get that idea of how it works, where you take those incremental steps and then you add like a dy to it and stuff. That's just the idea. The rest of these are a little bit more complicated, where they have like neat little tricks where you can take track of like the second derivative, the first derivative, and like this way and that way, and it makes it better. So this is another example. This is a modified version of the Euler method called the symplectic Euler method. That method preserves phase space volumes. If you don't know what that means, you should take 105. It's interesting. It's like really interesting mathematical structure and stuff on how mechanics works. But it allows it makes a much better approximation for a lot less of numerical cost. So you can see the circles are actually like pretty well defined, like they're like stable semi. But look at the energy. That's bad. That's like oscillating. I mean, at least it's oscillating and staying like on average the same, but it's not like, you still wouldn't want that, right? Like you don't want it to oscillate like that. Not a good look. Not reliable. I would not trust that to land my rocket on a planet. If I was predicting their orbits. It's kind of better, but it's not that great. I just wanted to show you that there is a modified version of Euler that is better. And if you're curious, you can come talk to me about it. But you'll probably see it in like 105 if you take 105, or if you go to like take physics 77 or something, they talk a little bit more about this kind of stuff. But there's a better one. It's called Runge-Kutta methods. Yeah. So let me explain it a little bit. It's the same idea of like the numerical, like taking the steps and everything, but it's like a bit more sophisticated. There's a lot more going on. I'm not going to explain it in detail, but I just want to show you how much better it is. We get like pretty much a pretty constant orbit around that star with only 200 steps. Before we were taking 100,000 steps to get anywhere near this. Oh yeah, and then the energy is actually constant, basically, like to like 0.001 precision or something. So Runge-Kutta is way more efficient, and it's energy preserving, which is like actually a lot more meaningful for physics. If you want to rely on that physics calculation, you probably should use a Runge-Kutta method. Again, I'm not going to go through the details. That'll be in another class, I'm sure, like in another upper division physics class or another coding physics class if you want to take that. I just want to show you that they exist. These are kind of the standard methods that you can use. And like, just so if you hear Runge-Kutta methods, just know they're solving differential equations. That's all that means, in a much more efficient way. So any questions? Okay, cool, we're on time. Did I record? I hope I'm recording. That would be so awkward if I wasn't. Should we check? Okay, I am recording. Woo. Okay, good. Oh man, I can't tell you how many times I've done that where I wasn't recording. Okay, so then of course SciPy does it better. They always do it better because that was their job. Like they're like working with Python. They like code it so well and like so well integrated with Python that it's like, yeah, you should always trust SciPy, at least in my opinion. They're paid to code that stuff and make it reliable. So we're going to use SciPy's version of these things. So this is just a function from the SciPy library, the integration library, scipy.integrate import ODE int. This is actually outdated. I found this out today, but I didn't have time to update the slide and all the resources that depend on this function. So just know it's a little out of date, but it still works fine. It's actually a function that uses another language called Fortran. It's like a wrapper around Fortran. That's like the shit they put the astronauts on the moon with. They like used the program. Fortran's like hella old. This like wraps around that. So like inside of that function, like the actual code has like calls to like Fortran code and stuff. So they updated it. It's a lot different now. There's different functions you can use, and I encourage you to go on SciPy and check it out. But we're still going to use this. It works just fine. Just a little different than the new methods, but learning how to use this, you'll be just fine learning how to do all the other functions as well. So with ODE int, it takes really three main arguments that are important. It takes a func argument, which is short for function. That's like the derivative. So it's like it takes your derivative function that you want to calculate with. So in this case, if you have like a function, a variable y and a variable t, it should take in y and t and compute the derivative. Yeah, make sure y is the first variable. Y naught is your initial condition on y. And then t is like the time at which you want to evaluate it. So if y is a function of t, this is like the time you want to evaluate y of t. Yeah, and this can be an array. So like you can actually like make it a whole list of or array of times, and it will evaluate at every time step. And the documentation's here. You can click on this link. And I don't know if it'll open it up. Yeah. And you can like, there's a whole bunch of other arguments that are super not important. And there's linked to other functions that do the same thing basically. But just in case you're curious, there's that. But yeah, ODE int is just a function, takes in a derivative function that you compute the derivative for like using an initial condition and the time at which you want to, or like the independent variable you want to take your derivative or evaluate your derivatives with respect. There we go. Can't speak today. And then if you want to learn PDEs, like I said, take another class. It's out of my pay grade. I don't get paid, so yeah. Well, I'm not going to teach you how to do that, but there are really cool classes to do that, and it's really, really cool the stuff you can do with PDEs. You can like see how heat evolves over time. You can simulate fluids moving through like stars and all sorts of cool stuff. All the cool stuff is with PDEs. If you're curious, come talk to me about it. It's not the end of week 7 just yet. We have to get into today's demo. So it was on Beat Courses under files. You should have seen it. I sent out an announcement under lecture demos. It's differential equations, this one. Go ahead and open that up. I'm just gonna open it up right here. I was working on it here last. Yeah, here we go. Where'd it go? Oh no, my bad. It was not on that one. It was on this one. Give me just a sec. This is why I like using Anaconda, because it's a lot faster. All right. DeCal. Here we go. Okay. Can everybody see this? Yeah. Okay, cool. And the people on Zoom should still also be able to see this, I think. Yeah, we're still recording. Okay, so do our usual. We got to import NumPy and matplotlib. Those are our babies. We love them. We'll also import SciPy in a minute. But just going through this, feel free to open this up on your own notebook or on your own laptop. To solve differential equations, we're gonna like start with the Euler's method. I'll let you like really go through the math for yourself if you're curious. It's also I put a link to, I believe I put a link to Wikipedia if you want to read about it in a little bit more detail. It's extremely inaccurate, and if you're using like Euler's method for your final project or whatever, you should totally let people know that you're using it so that they know not to trust it. In my opinion, unless you're using some ungodly amount of steps, but I don't like the Euler method, in case you couldn't tell. But it does give a good idea of how these things work. So you start the initial value problems by simulating the system using finite differences like we did for differentiation. For example, like here's an equation of motion. The second derivative with respect to time of x is like, you can think of that as x double dot. If you've taken like your physics classes, hopefully you've seen that notation. The dot on top of a variable means like however many times you take the derivative with respect to time. This is just a function of like x dot and x and t. So it can be like, you can have like x double dot plus x dot plus x or t or whatever. It's like second order differential equation. And the initial conditions for x and x dot, we need to have those. Like you can like discretize time and update x and x dot with each step. So I'll let you read through this on your own time if you're curious, but it's the same, it's the exact same thing we discussed on the slide. So same idea, same principle and everything. But now we're just doing it for a second order differential equation. So we need two initial conditions. Before we have like an x naught, y naught or whatever. Now we have like x naught and v naught, at least in this example. So we define a function called Euler method. N is just like the length of like the number of steps we want to iterate over. X, we start with like, in this case, we like, there's always different ways to implement it. This is just one of many ways. I encourage you to try doing it from scratch if you want. I'm sure you'll get homework with this or experience with this a little bit more in your homework. But nonetheless, this is just how we happen to implement it in this function. You start with like a bunch of zeros for x and v that are like an array of length n. You start with some initial conditions, x naught, v naught, and then you just use a for loop to iterate from like we put those x naught, v naught as like the 0th element, and then we iterate from 1 to the end of the arrays. You know, updating time by taking the difference between the current step in time and the previous step in time, and then doing the same thing with x times dt, and then v times your derivative with that takes in x and v and t with respect to time, or x like multiplied by dt. So fn is a function that you specify. So fn is like the same idea as like the func derivative in like the SciPy or the SciPy integrate or SciPy.solve ODE int function. Fn is like a function that you can customize yourself. So this won't know how to solve anything unless you give it a function and initial conditions and a length of, or like a scale of time, or like an array of time steps you want to iterate over. And it computes this, it gives you x's and v's, and then x and v are arrays of values of the values that you've updated through the time steps. So if we run this, yep, cool, we have that. Now we have that function at our disposal to do the Euler method. Again, you can go through this on your own time to kind of read through it and hopefully understand it a little bit better. But remember, energy is not conserved by the Euler method. For like a simple harmonic oscillator, for example, the second derivative with respect to time is equal to negative omega squared x. Hopefully you remember that from your 5A, 7A classes maybe, or high school physics if you're taking that. So we have this differential equation that represents how a spring moves, and it oscillates at some frequency omega, which should be the square root of k over m. And then here's a cool GIF of a spring. I'm really proud of it. I got it from Wikipedia. But we know that energy conservation should stay constant. So like the total energy of the system should stay the same if there's no friction or anything. It's just an ideal spring moving. And that should be equal to like 1/2 mv squared plus 1/2 kx squared, because you can have some energy stored in the spring, and then you have some energy from motion, like kinetic energy. Okay, so we have potential plus kinetic energy should be a constant. So we can code this in. We compute like a function called restoring force, which basically is the derivative function. The restoring force is the derivative function that I was talking about earlier, that Fn. So we're gonna plug this in to our Euler method function. We specified like our x naught and our y naught. We say what omega is so that it's defined. We have like a t max value, and then we create essentially here. We create like an array of times that we want to evaluate over. So 0 to t max, taking however many steps. In this case, we do like 10 to the 3, 10 to the 4, 10 to the 5 steps. Just all those different kinds of steps, or all those different numbers of steps. And we're going to plot the trajectories. You'll see what I mean in a second. Then you like call this Euler method function, giving an initial conditions and a derivative function, and then the array of times, and it'll give you a whole array of position and velocity values. And then you can compute the energy from those values, and then we'll get something that looks like this. Takes a minute because we're doing a lot. And we see this. So On the left side is 10 to the 3 steps, middle is 10 to the 4 steps, right side is 10 to the 5 steps. Okay. Holy shit, the left one is bad. Your spring like keeps getting bigger. Like, it goes out to infinity. That's not good. You do not want a spring that does that. At least the middle and the right one look reasonable. They look like they're kind of constant. Middle one's definitely growing a little bit though, if you look closely. But the real sure sign that this is absolutely awful is the energy. That energy is like legit going up, like exponentially. No, it should be a constant line. Both of these are linear. That's bad. So we use the reliable, old faithful SciPy ODE int to do this. It's a little confusing the way they wrote it. I'm not gonna lie. If I was writing the function, I'd probably write it a little differently. So bear with me. This will be something that you just kind of have to work with on the homework assignments to like really understand it and read the documentation closely. But with SciPy's integrate ODE function, you have your like your derivative, like your differential equation function, du dx. The way we write it is that u is a vector that contains both like the initial conditions, u0 and u1. Well, it's not the initial conditions, but it contains like the 0th element of u is your y, and the first element of your u is z. And we define y, or we define z to be like the derivative of y, so y prime. And then this function should return y prime and z prime, aka the derivative of y and the second derivative of y. Pretty sure. So the second derivative of y, going back to this, is negative omega squared x. Sorry, we're switching between x's and y. They're the same thing. X and y are the same thing. We're just following the standard convention for this function. But the second derivative is negative omega squared x. And in this case, it'll be a y, but negative omega squared y. That's like your second derivative. And then your first derivative is just y prime, which is what we define z to be. Cool. You give it some initial conditions, u not. So we're saying start at a y value of 0 and start at a velocity of 1 or whatever. And then we iterate, we want to do 200 steps between 0 and 120 seconds is like our X array. And then we just get a whole array of values, kind of like how the Euler one works, where it gives you your velocities and positions. We just plug in this function. We plug in our initial condition array or list, and then the X is going to do it over. And then in this case, we only want the Y values. So we take we iterate it, or we select those values out of the output of US. So it should be an entire list of values corresponding to like the Y values only. Might be Y primes. I can't remember exactly. This function confuses me, but I encourage you to look at it. It's really well explained in the homework. I believe we'll have like a really good problem on that shows how to animate later. You'll get more practice with this. But anyway, if we plot it, huzzah, look at that. Euler is good in all, but SciPy does it better in like half the computing time, power. And this is an Euler step with, I think I chose like 1 million or 10 million steps. So you can see like SciPy uses it in like barely any steps. And Euler, wait, how many steps did we take for this? We took 200 steps, 200 iterations, and we get this. Whereas Euler took 1 million steps and got basically the same thing. So it's a much, much more efficient and more reliable. I didn't plot the energy because I didn't have time, sorry. But I encourage you to try it if you want. You can also plot the energy and see how it looks. But anyway, the takeaway is that you should use SciPy ODE int if you want to trust the results. Use Euler if you just want to make a pretty plot. Yeah, and that's everything I wanted to share today. Homework 6 will be due next week. It should be announced today. And I think we're caught up with lecture videos and slides, so all that should be available on B courses. And don't forget, this was kind of a last minute post. Yes, last lecture. The debugging guide is available for you to check out. It is super cool. I can actually show you really quickly. Really quickly. I know your time is precious. and you want to get out of here. But debugging guide. It looks like this. It was made by me, Maham, and Megan. It's very cool. It walks you through how to debug. So when your code breaks, how do you fix it? And it walks through a whole bunch of examples on how to read those giant error statements that are confusing, how to Google stuff, how to predict errors. So like when you expect your user to like add some code and then break it, or if they like, if your code takes in inputs, how do you expect them to do bad things that might break the code? So then you tell them, hey, cut that out and do good things. There's things called try and accept loops or conditionals that are really good. Summaries. We have literally, I think almost every error we could possibly think of. We show you like how to fix that kind of error. Props to Maham for going through all those errors. Hopefully she's somewhere in the crowd. Maybe not. She was earlier. I don't know where she is now, but whatever. Yeah, and like anticipating errors. So I highly encourage you to check it out. If you don't know how to fix your code, you should take a look at this guide. It's really helpful. We put a lot of effort into it. Yeah, I think that's everything I want to share today. Week 7's over. Oh yeah, there's Maham. You can give props to Maham and Megan back there too. Cool. All right, I'll see y'all next week. Wait, where is it?
I realized someone from Fox is doing a spot check of our COVID policies, so I have to go.
What? Okay.
Yeah.
Oh,
They're
there.
coming to check that we enforce the green bag.